All right, welcome to the Explainer. Today we're diving deep into the world of power diodes. Now, you might not think about them much, but these things are the unsung heroes controlling the flow of electricity in, well, pretty much everything, from your phone charger all the way up to an electric car. And how they've evolved, it's a really fascinating story of engineering trade-offs. Okay, so just take a look at this. Right off the bat, you can see this huge variety of shapes and sizes. You've got these tiny little components, surface mount packages, and then, wow, these massive industrial pucks and stud-mounted diodes. They couldn't look more different, right? But believe it or not, they all do the same fundamental job. They just happen to be good at it in very, very different ways.
So, to really get why there are so many different kinds, you have to understand something we call the engineer's dilemma. See, in a perfect world, what an engineer wants is a diode that's basically a superhero. It switches instantly, it can block any voltage you throw at it, and it loses absolutely zero energy. The problem? That perfect diode, well, it just doesn't exist. It's this constant battle, this balancing act between all those things.
So, today, we're going to follow that story of innovation. We'll see exactly how engineers tried to solve this problem, step by step. We'll start with that core dilemma, then we'll meet the original silicone workhorse, follow the quest for more speed, witness a genuine material revolution, and finally, see how it all comes together in the ultimate combination.
Right, so the main thing to get here is that this perfect diode, the one that's super fast, blocks tons of voltage, and has zero energy loss, it's a fantasy. It just doesn't exist in the real world. Every single choice a designer makes is a trade-off. You make it faster, you probably sacrifice how much voltage it can handle. It's always a compromise.
And that whole challenge, it brings us right to our starting point, the original high-power solution. Think back to a time when the main goal was just to handle a ton of power at low frequencies, like the electricity coming out of your wall socket. For that job, engineers developed a real beast of a component.
And here it is. Meet the general-purpose diode. This is the original high-power workhorse, and it was optimized for one thing: handling huge currents and voltages. We're talking raw strength. It was perfect for things like rectifying the power from the grid or in big, uninterruptible power supplies. Its job was to block a lot of voltage and not lose much energy while it was on. And that's it. Speed wasn't even really part of the conversation yet.
But, and this is a big but, it has a critical weakness. Its reverse recovery time, that's the time it takes to switch from on to off, is around 25 microseconds. Now for low-frequency jobs, who cares, right? That's totally fine. But for modern, high-frequency circuits, like the power supplies in all our gadgets, 25 microseconds is an absolute eternity. It would waste a ton of energy as heat, making it completely useless for those applications. So that need for speed, which was really driven by the rise of more and more advanced electronics, it sparked the first major leaps in diode design. That 25 microsecond bottleneck, it just had to be broken. And engineers, well, they came up with a couple of really brilliant solutions. Okay, solution number one, the fast recovery diode. Now, this wasn't a totally new design. Instead, engineers got clever and they optimized the traditional PN junction itself. They figured out how to minimize this thing called stored charge. You can think of it like residue that's left over when the diode is on. You have to clean it up before you can turn it off, and that's what slows things down. So they found a way to leave less of a mess.
And the improvement was, wow, it was dramatic. Just look at this. We went from that 25 microsecond recovery time all the way down to less than 5 microseconds. That is a huge leap forward. And it's what really enabled all the efficient, high-frequency power circuits that we totally rely on today.
But engineers, they didn't stop there. The next step was to completely rethink the whole structure. They started asking, what if we could get rid of that stored charge problem, like almost entirely? And that question led to a totally new blueprint, the Schottky diode.
See, this thing is built differently. It's a metal-on-semiconductor design, and that creates something called a Schottky barrier. The way electricity flows through it is just cleaner. It creates virtually no stored charge to clean up. And what does that mean? Near instant switching and way better efficiency. But remember that dilemma we talked about? Here's the trade-off. Your standard silicon Schottky diode just can't block nearly as much voltage as its old-school cousins. So now, engineers had hit a kind of fundamental roadblock, a wall. They'd optimized the old junction, and they'd come up with a whole new structure,
But to get the best of both worlds, to get that high speed and high voltage, they were going to need something, well, truly revolutionary.
And that led them to ask a really big question. What if the problem isn't the design anymore? What if the problem is the silicon itself? I mean, for decades, silicon was the undisputed king of semiconductors, right? But to get past this barrier, maybe it was time to look for a new king.
And the answer was, yeah, change the material entirely. Everybody meet silicon carbide, or SiC for short. This stuff is what's known as a wide bandgap semiconductor, and its properties are just fundamentally superior to silicon for this job. It can handle way stronger electric fields, which means higher blocking voltages, it can run at much hotter temperatures, so it's more rugged, and it's way better at getting rid of heat.
And this visual just illustrates the difference perfectly. Look at that big blue area. That's all the stored charge in a regular silicon diode when it turns off. Every bit of that is wasted energy, just lost as heat. Now look at the tiny little orange line for the SiC diode. The stored charge, the switching loss, it's practically nothing. It's almost negligible. This isn't just an improvement, folks. This is completely transformative. So, this material revolution, it really was the final piece of the puzzle. It finally allowed engineers to combine the best of both worlds. They could take that clever Schottky structure they'd already invented and pair it with a material that could unlock its absolute full potential.
And what you get is the SiC-Schottky diode. It merges that revolutionary structure with the revolutionary material. So now you get the crazy fast, near-instant switching of the Schottky design. But because it's made of silicon carbide, you also get the high blocking voltage and the rugged high-temp performance that the old silicon version was missing. It's the whole package.
And this powerful combination is what makes the high-power, high-frequency systems that are literally defining our future possible. We're talking about the guts of EV fast chargers, the inverters that make solar power practical, and the next-gen industrial power supplies. And why does this matter to you? Well, higher efficiency means less wasted heat, and that allows for smaller, cooler, and much more reliable electronics for all of us.
So, this is a great way to put it all together. It's like a designer's cheat sheet. You can see exactly how each type of diode offers a unique solution to that engineering dilemma we started with. Need cheap, high power for low frequencies? Go with the general-purpose workhorse. Need more speed? You've got fast recovery or a regular silicon Schottky. But if you need it all, the speed, the high voltage, and the top-tier efficiency, then the SiC Schottky is, without a doubt, the ultimate choice.
So when you boil it all down, the story of the modern power diode is really a story of three huge evolutionary leaps. First, engineers optimized what they already had, the p-n junction, to make it faster. Then, they completely redefined the structure with the Schottky barrier to get rid of switching delays. And finally, they revolutionized the material itself using silicon carbide to shatter those old trade-offs and hit a whole new level of performance.
And that brings us right back to where we started, doesn't it? It's all about that constant search for the perfect balance between these competing demands. And you know what? This evolution, it never really stops. Why? Because our demands for better technology, they never stop growing either.
Which leaves us with a really fascinating question to think about for the future of electronics. You know, we went from silicon to silicon carbide. So, what's next? As we keep pushing for more and more power in smaller and more efficient packages, what do you think is going to be the next new material or the next radical new structure that drives the next great leap forward?
Thanks so much for joining me for this explainer.